Hi. It was Biweekly Challenge 32 yesterday on Leetcode. We could not solve the find longest awesome substring question in the Think Out Loud. We are going to continue the Think Out Loud. This is the part two of it. We're going to read the discussions and we're going to try to figure out where we went wrong. So basically, let me just switch to the direct question link. Yeah. So basically, we did most likely get the answer right, but we could not do it within the time limit. We were getting a TLE error. So we're going to try to figure out if our approach was right and if how to do it. I'm also going to post the editorial if you don't want to go through the thinking and trying to figure out how to understand the editorial, then please just go there and understand it. This might help you to learn how to read discussions, how to understand them by yourself. And yeah, I'm just going to think out loud understanding. All right. So let's have a look. Since the contest was yesterday, a lot of people have posted discussions, and we might even be able to find some interesting ones. We're going to sort them by the most votes. C++, Java, Python 3 with pictures similar to 1371. All right, let's just open this. It has 65 votes and 1.2 thousand views. I think this might just work. All right, let it load. All right, feel free to check out this question. We're just gonna go ahead and see it. All right, so let me just quickly give you a brief of the question in case you don't remember it. So basically, we're given a string. We want to find a substring, and we want to find a substring such that allowed any number of swaps, we can make it a palindrome. So it should just have the characters which can be converted to a palindrome. And we want to choose the longest such substring. That would be our awesome substring. All right. Let's check the discussion. This one. We can form a palindrome if the count of each included number except maybe one is even, then and this is the property of an awesome string. So we got this. We were checking the counts and we knew that odd can be at max one, and if it's true, then we'll have a palindrome. A bit in our mask is 0 if the count of the corresponding number is even, and 1 if it's odd. Okay. As we go through the string, we track odd, even counts in our mask. If we see the same mask again, the subarray between the first position exclusive and the current position inclusive with the same mask has all the numbers with even count. Alright, so I don't understand this. Let's read it again. We're doing a bit mask, which is a popular approach. I haven't had much experience with it. A bit in our mask is 0 if the count for corresponding number is even. Okay. So probably they're having a bit in the mask, they're having a bit for each character or each number only from 0 to 9, and they're going to keep updating it, I feel. Okay, so that makes sense, right? What we were doing was we were maintaining counts, and we were checking the count each time and updating it and doing a prefix sum and all, but we don't need the count as such. We just need to check whether or not the count is odd or even, and whether the count is odd or even can be represented by just a single bit. And every time you encounter the number again, if it was odd, then the count would become even, and if it was even earlier, the count, then it would become odd. So we just need to flip the bit whenever we encounter it, and at the end we'd have the counts order even in our bit mask. I think that's what they're trying to do. If the count for the corresponding number is even and one if it's odd as we go through the string. So at in the starting we're going to have all zeros probably. As we go through the string we track odd even counts in our mask, right? If we see mask, the same mask again. Okay. So this is kind of, so what they're doing is something like a prefix sum, but instead of a prefix sum, it's like a prefix mask, in my opinion. So at each point, you know whether the counts up till that point have been odd or even, and they see whether the mask repeats. So if counts of all digits in at position I were like 10111, if we're just checking, if we're having only digits from 1 2 3 4 5, so we've only 5. Now a 5 place mask can be, one example can be 10111. So if we have 10111 at ith position and at a future position j, suppose we encounter the same mask 10111, then we need to check something. And 10111 means that 1 has odd number of occurrences, 2 has even number of occurrences, 3 has odd number of occurrences, 4 has odd number of occurrences, and 5 has a odd number of occurrences. Alright, so if we see the same mask again, the subarray between the first position, exclusive, and the current position, inclusive. So from I plus 1 till j, because I and j are the bounds and I is exclusive and j is inclusive, so from I plus 1 to j essentially. The subarray between I plus 1 and j with the same mask has all the numbers with the even count. Alright, so okay, this makes sense. So basically, we encountered the same mask at two positions. This can only happen if we have even counts of all the numbers added, because if you add an odd count, then the number from odd becomes to even and from even it becomes to odd. So if we have the same mask at two places, then it definitely means that all the numbers occurring between these two places were added a even count. And we can't include the first one because, yeah, because the first index was from all the indices up to that place or something like that. So we need to check what happened after that. So only the index after it. We'll use dparray to track the smallest first position of each mask. We can get the size of substring by subtracting it from the current position. Okay. So we'll use a dparray to track the smallest first position of each mask. Okay. So they're using mask as keys in a dictionary probably. We, in terms of Python of course, and we can get the size of the substring by subtracting it from the current position. Note that position for 0 mask is -1 as we need to include the very first character. Okay, now the difference from 1371 is that a palindrome can have up to one number without count. Therefore, we need to also check all the masks that are different from the current one by 1 bit. In other words, if two masks are different by 1 bit, that means that there is an odd count in the substring. Okay. So that makes sense. So they're saying that we have the bit masks for all of these places. Now we don't just need to consider when that same bit mask occurred again, but we also need to consider the case when a similar bit mask occurred again, and a similar one means that all the bits are same except one. All right, then they have the string as 10221, and in the beginning they have mask 000. When you add 1, oh, so they've used just 0, 1, and 2 to keep things simple, and the mask would be of length 3. So 0, 1, 0, this becomes odd. 0, 1, 1, 0, 1, 1, is it? We were encountered with a 0, right? So 0 probably takes the last bit for them. Yeah, because that's the first bit. Okay, sorry, my bad. So this is for 0, this is for 1, this is for 2, because this is the lowest, least significant bit. So that's what they're doing. Okay. So 0, 1, 1, then 2 becomes 1, 1, 1, 2 again, this become bit flips again, 1, this bit flips again. Okay, cool. So these would be the bit masks at these places. Now, 0, 0, 0 occurred for the first time here, 0, 1, 0 occurred first time, 0, 1, 1 occurred first time. Um, 0, 1, 1 occurs here again, right? That's why they do a yellow shade here. And 011 and 010 has a 1 bit difference, so that's why they do it here like this. Okay, 001 and 111, I'm not sure what they mean by that. 001 occurred for the first time here. Okay, and 001 can match with 000 because it's a 1 bit difference, and it can also match with 011. Okay. Okay. Alright, so I get the idea, but I'm still not sure how they're gonna code for it. Let's have a look at the code and try to understand what they're doing here. So it's a very small code. Okay. Mask starts as zero. Result also starts as 0. DP is -1 plus length of s into 1023. Okay, what did DP store? The smallest position of each mask. Okay, so we're gonna have a 10-bit mask, so 2 into 10 to the power 10 is 1024. So okay, what are they doing here again? Suppose s is of length 5, then they have 5 1023 times and a -1, and that's deep. Okay, so probably what they're doing is that they're not storing bit mask as a character wise 0 1 sequence, but they're storing it as an integer, which would be much more efficient to store, but much harder for me to understand. At least I'm not sure about you guys, but this is the first time I'm trying to understand this, so it's a bit difficult, but that's the idea, I think. So okay, they said the first occurrence of in the bit mask bit mask of 0 0 0 0 10 times is going to occur at the -1 position, so that's why the first element in DP is -1. Now the next bit mask will be 0 0 0 0 0 0 0 8 times, 9 times, and a 1. And then it would be all zeros, then ending with the 1 0, something like that. Then all zeros ending with the 1 1, and so on. So all of those bit masks, they set it as the length of the string. So that's because the position that it occurs on, they're considering it as the index at which it occurs, and length of s is an index greater than all the possible indices, because length of s is not a valid index in s, because the indices are from 0 to s minus 1, right? So they initialize the first bitmap's occurrence to -1 and all the others to something which is greater than anything that can occur. And then they iterate over all the elements in S. Okay. Then they do something very interesting. Okay. So I feel this is probably just converting that character to the corresponding. Okay. Long one. Okay. Yeah, we have it here. So we're just gonna check this real quick. Can't increase the size somehow. Oh, okay, my bad. Yeah, this should be better. All right, cool. So, what just happened? Yeah, okay. So, odd of a character, say 6 minus 48. I think this would be 6. Right. So, because ASCII of 0 would be 48, in my opinion. Yeah, okay. So, they convert the character to the number here, and they do a 1. They shift 1 by that many places. So this would be 1 followed by 4 zeros, or 5 zeros. 5 zeros, I guess. Because if you do this, you would get 1. If you do this, yeah. So 1 followed by 5 zeros, that's what we're getting. So that's like the one hot encoding, I feel. Yeah, that's the one hot encoding of that number, right? So if you have, so the bit mask would look something like this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we have 5, then it's going to do that, that you have 5 zeros, 1, 2, 3, 4, 5. And then you have a 1 here. And if you convert this to decimal, it would be 2, 4, 8, 16, 32. Exactly what it said. So it's converting our character to an integer, and that integer to the corresponding one hot encoding, and then doing a XOR with the mask. So a 0 would become a 1, and a 1 would become a 0. Okay, interesting. That's a lot of code just compressed into one line. Very interesting. Okay, so that's what it's doing. Taking the one hot encoding, representing it as decimal, then doing a XOR with the mask so that we update the mask, and updating the mask means that we just converting the count from odd to even, and if it was even, then we're converting it back to odd. All right, not necessarily back to odd, it can be starting with a even and then a odd for the first time. All right, so for j in range 11. Okay, so for each of the bit mask places 0 to 10, check mask equal to 1023 and mask XOR 1J. Okay, what is it doing? Alright, let's think about it again. So 1023 would be all ones, right? It would be 1 10 times because 1024 is 1 followed by 10 zeros. Yeah, so it would be all ones. So it's taking all ones and then 1 and pushing it left by j places. So that would be the one hot encoding of that position. So for each position, it's taking the one hot encoding, doing a XOR. Okay, so I think I understand what it's trying to do. So it's saying that we had to check whether the mask that we get in the future is at most one position different. So I think that's what they're doing. They're trying to differ it by one position, one bit. So for each bit, they flip it and then they do it as a AND with 1023. I'm not sure why do they do that. AND with the 1023 would just give the very same thing, right? Because those are all ones and 1 and 0 is 0 and 1 and 1 is 1. So why do you need to do that? Let's see if anyone has put a comment regarding this. No, there are only 6 comments and they don't seem to be here. Alright, so I'm not sure. I'd probably have to check with code. Yeah, I'm unsure about this. Ah, okay. What? So our bit mask would be 10 bit long, right? But J goes from 0 to 10, which is 11 numbers. And okay. I think I understand what he's trying to do. Okay, that was smart. That was super smart. So basically, this 1023 and would not have any significance for all the numbers from 0 to 9. But when j takes the value of 10, then that is 1, 10. That is 1024. Now, 1024, if you AND that with 1023, okay, my bad, 1024, and you AND that with 1023, you get a 0. So that is to check that both of the bitmaps are same, because the mask only has 10 places and 1 dash dash 10 has 11 places, so technically we'd add 1024 to whatever the number is, but when we add it with 1023, we get the same mask back. And just to compress the number of lines of code, this is just very nicely written and very nicely compressed. Makes it harder to understand, in my opinion, but then I guess people who've a lot of practice of all this just know how to just compress it and not be have to write everything, and they still understand it very easily. So we'd reach there one day. We're gonna go together, my viewers and me, and we're gonna grow and figure it out. Yeah, I have confidence in us. All right. So they changed the mask by 1 bit. They keep the same mask and they change every position by 1 bit. That's what the 11 signifies. Change all the 10 positions and also keep it same. Check mask has all of them covered. Now res equal to max of res I minus dp of check mask. Okay. So alright, so what did it do? Ah, okay. Now I understand it. So neat. Again, this code just very interesting. So basically, what happens is that the current position that we are at is I. Current index that we are at is I. We're subtracting I. We're subtracting this from I, dp of check mask. Now, what we're doing is that we are at index I. Check mask is not what's going to appear in the future, but what has already appeared in past. So for this position, we're going to check all the past possible bitmaps that we can match it with, and all the past possible bitmaps that we can check it with are in checkmask. One by one, it's going to take all that values. Now, all those possible past bitmaps that we have to check it with, dp of that possible bitmask is gonna have the index of the first occurrence of that bitmask, and we set initialized it with the length of the string. So if it has not occurred, then this would be negative, and we start with the result as positive, result as 0. So it is never going to take a negative value. So if and only if it has occurred in the past, then it is going to do this, that it goes, it takes this place, subtracts the past place, and updates res with it if it's greater than the previous value stored in res. And what it also does after doing this is that update the mask, update the dp of mask by the minimum of dp mask and I. So we initialize that with the end of the indices. So if it occurs at any index, then it's going to take that. If it has already occurred, then it would not change it, because if it has already occurred, it's already lower, and it's just going to store that index in dp mask. And we do that after this iteration, but I think even if we moved this thing up, it might have still, it would have still worked, right? Because what would have happened, right? Only this would have changed if it had never occurred before, and this would just do a I minus I, and that would be a 0. So I don't think it would have mattered. We could have done this here, or we could have even done this after this line. So, and then it returns res at last. That makes sense, right? Now res we know for a fact would be 1 always, because no matter what you do, no matter what string you have, if the string length is um, if the string length is at least 1, then the palindrome which can be made can be 1. So let me just check this. So solution dot longest awesome, and we're gonna give it as a 1 2 3 4 5 6 7 8 9 0, and check. It should give us 1, right? So missing one positional argument. Okay, so I'm always bad with this stuff. So do we need to declare this solution? Yeah, probably. So we're gonna have a solution s equal to solution, perhaps, and then use s dot longest awesome, and then do this. Yeah, so we did it. So basically what it would be doing is at this position, check the bit mask. All the checked bit masks would also match. One of them would match at the previous position, and that would be this position minus previous position, right? Yeah, which would be 1. And we also do it for the first one because we initialize this as -1. So 0 minus. Okay, so we initialize it as -1 because um, if we have something like just this, man, this is just awesome. All of every single thing in this code has some significance. So just this would also give us 1, and the reason it does that is when it checks for past occurrences of bit masks, it also checks for all zeros, which occurs at -1 as we had configured it in DP. Now it occurs at -1, so it's going to do the current position 0 minus of -1, which is going to give 1. So fabulous. Time complexity analysis is order of nk, where k is the number of unique characters we track, which would be 10. So it is an order of n solution. We go through the string once and do k checks for each character. Right. Wow, this is the order of n solution. That's awesome. Memory is order of 2 to the power k, where k is the number of unique characters we track. Because why? Because bitmask is not going to take that much memory. Perhaps no, it would. So 2 to the power k, because DP also has that. Right? DP has that many k many yeah, that many elements. So for each position, we are storing position of all possible bitmaps at 2 to the power k, that is in our case 1024. So that's the length of DP. So that's the amount of memory used. Alright, so we've successfully understood it. Thanks a lot for sticking with me and trying to figure out and trying to understand what's written here. I'm gonna make a tutorial video which is gonna be a very quick recap of this very solution. Feel free to check that out if you want TLDR, or if you want a recap of everything that was done in this video. You would find the link below in the description. Please feel free to write your suggestions and comments in the comment section below. I would make sure to acknowledge and try to accommodate it. Bye. See you next time.